this video, we are going to discuss the solution for UGC NET paper for December 2020 and June 2021 for the subject Electronic Science. In Electronic Science, we have a subject called Digital Electronics, and from Digital Electronics, we had around 7 questions in this question paper. So we are going to discuss these questions in this video. And one more thing, I have selected the questions from the previous year paper, that means 2020 and 21 paper, from the official website of UGC NET and TA. And according to that, they have released the answer key as well. So like this, they have given the question ID and correct answer. But some of the given answers are incorrect. So in this video, we will discuss which answer is going to be correct. So this is the first question that we have to discuss. A single bit comparator compares two numbers A and B and produces 3 outputs. First output is Y1 when A is equals to B. Second output is Y2 when A is greater than B. And third output is Y3 when A is less than B. According to that, we have different logics for Y1, Y2 and Y3. So we have to select the given option which is going to be correct according to the given options. So let us solve this question. So in combinational circuit, we have studied the topic that is called as comparator. So comparator is basically a combinational circuit in which it is going to compare two numbers of single bit. So A and B both are single bit numbers. And we have 3 output: Y1 when A is equals to B, Y2 when A is greater than B, and Y3 when A is less than B. Now we can write different combinations for A and B, that is 0, 0, 0, 1, 1, 0 and 1, 1. According to that, we have to write when logic will be high or low for Y1, Y2 or Y3. So consider the case 1 when A and B both are 0. So in this case, A and B both are same, so Y1 will be 1. In the second case, A is not equals to B, it is actually less than B. So this is going to be logic 0. In the third case, A is 1 and B is 0, so it is greater than B. So in this case, Y1 is going to be 0. In the fourth case, A is 1 and B is also 1, that means both are same, so Y1 will be logic 1. So according to that, if we write the logical expression for Y1, so this stands for A bar, B bar, and this stands for a minterm A into B. So if we write expression for Y1, this will be A bar, B bar plus AB. So we can write Y1 as a summation of these minterms, that is A bar, B bar plus AB, which is nothing but expression of a XNOR gate. So that will be A XNOR B. So Y1 will be equals to A XNOR B. Now we can write for Y2. Y2 is a condition when A is greater than B. So in the first case, A is same as B because both are 0. So this is going to be logic 0. In the second case, A is 0 and B is 1, which is, we can say A is less than B. So it will be logic 0 because the condition is A greater than B. In the third case, A is 1 and B is 0 and the condition is satisfied because it is A greater than B here. So this is going to be logic 1. In the last case again, A and B both are same as 1. So for this case, Y2 will be 0. So if we have to write the expression of Y2, so this is a minterm corresponding to this one will be A into B bar. So we can write Y2 from here as A into B bar. This is the expression for Y2 of this comparator. Now let us write the expression for Y3. So if we consider the first case, when A and B both are 0, this is going to be 0 because the condition is A should be less than B. Second case, A is 0, B is 1, so this will be again, this is going to be 1 because in this case, A is less than B. In the third case, A is greater than B, so this will be 0. In the fourth case, both are 1, both are same, so this is going to be 0 again. And a minterm corresponding to this one will be A bar into B. So we can write Y3 as A bar into B. So we have obtained the expression for Y1 and Y2 and Y3. These are output of the comparator circuit. So if we have a comparator which has inputs as A and B and outputs are y1, y2 and y3, then expression for y1 is A XNOR B, y2 is A dot B bar and y3 is A bar dot B. So we have to select the correct answer from the given option. So from option A, you can say this is the right option because y1 is A XNOR B, y2 is A B bar and y3 is A bar B. So A option is correct. B option, if we check, this is incorrect. C option is also incorrect and D option is correct because y1 can be written in this format also. So these are two expressions for y1. So this is given in option number D and this is given in option number A. So from the given option we can say fourth option which says A and D only are the correct answer. But as you can see here, they have given the correct answer as A and B, which is incorrect. Okay, so correct answer will be option number 4 that says A and D are correct. Let us see the next question. The simplified Boolean expression for the following K-map to find function in SOP form. SOP stands for sum of product format. So we have to write the expression of f in terms of sum of product of the minterms. Okay, now this is the K-map. And now one thing you notice here that there is nothing written over here. But in the exam, there was 0 at this point. Okay, so this is a question, repeated question from GATE, ES. So it is a very, very important question asked in many different exams. And now it has been asked in UGC net. So let us make the K-map again. So this is the given K-map and now we have to make pairs of 1. So we have to make group of 1 as large as possible and we have to cover all the ones. That is the basic procedure of solving a K-map. So if we want to cover this one, only this is the pair that we can make and this stands for A bar into C into D. If we want to cover this one, this is the only pair that we can make and this stands for A bar B into C bar. If we want to cover this one, this is the only way of covering this one. So we can make a pair like this and this stands for A into C bar D. And if we want to cover this one, we need to pair these two ones and this stands for A dot B into C. Now you can see we can make another group that is group of 4 or we can call it as a chord. Okay, so we can make this chord. But before making this chord, let us check if all the ones are covered. Yes, all the ones are covered. So do we need to make this chord? No. So we don't need to make this chord. Okay. So let us write the expression of f that will be A C bar D plus A B C plus A bar C dot D plus A bar B dot C bar and a term that is representing the chord that is B into D, that is a redundant term. So it will not be written in the expression of f because using K-map we have to write the minimized expression. Minimized expression means it should get minimized and redundant term should be removed. So this is a redundant term and it must be removed from the expression. So from the given option, if I check, the fourth option is matching with this. Okay, but if you look at the answer key, they have mentioned this BD term also, which is a redundant term and that must be eliminated while writing the expression of f. So this is an incorrect answer given by the answer key. Okay, so the correct answer will be option number 4. Next question is, a number may be represented in various number systems. Arrange the following number system in ascending order based on the number of bits needed to represent the same number. Okay, so these are the four given number system: binary that has a base 2, decimal that has a base 10, hexadecimal that has a base 16 and octal that has a base 8. So we have to arrange these number system according to number of bits required to represent the same number. So for solving this question, we can take an example. We have to take any number. So let's consider number 80. 8096, and this number should be represented in the binary, decimal, hexadecimal and octal. So let us convert this number into different number systems. So 8096, this is in decimal. Now we want to convert this into octal that has a base 8. So for that we are going to use divide by 8 method. So this is 8096. Let us divide this by 8. So that will be 1 0 1 2 and the remainder will be 0. Now again divide it by 8, so that will be 1 2 6 and remainder will be 4. Again divided by 8, that will be 1 5 and remainder is going to be 6. Divided by 8 again, that will be 1 and remainder will be 7. Now we cannot divide 1 by 8, so that will be 0 and remainder will be 1. So 8096, that is in decimal, can be written in the octal format as 17640. This is our octal representation. Okay, so how many bits are required to represent this number in decimal? That is 4 bits are required. Here how many bits are required? 1 2 3 4 5. So to represent the same number in the octal format, we need 5 bits. Okay, now let us convert this number into hexadecimal. So for hexadecimal, the base is 16. So we are going to divide this number 8096 by 16. So this will be 506 and remainder will be 0. Divide it again by 16. So that will be 31 and remainder will be 10. And 10 in hexadecimal is written as A. Now again divided by 16, that will be 1 and remainder will be 15, and we know 15 in hexadecimal is written as capital F. Now again divided by 16, we cannot divide 1, so that will be 0 and remainder will be 1. So the given number 8096 in decimal can be written as 1FA in hexadecimal. And how many bits are required to represent this number? 3 bits, 1 2 and 3. So we need 3 bits to represent the same number in hexadecimal format. Let us now convert this given number into binary. Now divide by 2 method will be very lengthy. So what we can do, using this octal number, we can directly convert this octal into binary. For that, each number should be represented into binary format using 3 bits. So this will be 17640. So we can write it as 000. This will be 0 1 100. This will be 110 and this is going to be 111, and for this we need 001. Okay, we can remove these 2 zeros and this is the binary representation. So binary representation of this given number is 1111 110 100 and 000. So this is binary representation. Now how many bits are required? Don't need to even count this number. Okay, let's count this. 0 1 2 3 4 5 6 7 8 9 10 11 12 13. So we need 13 bits to represent this same number in the binary format. So we can arrange these numbers system according to number of bits required to represent the same number. So largest number of bits are required in case of binary, so that will be at the last. So binary is requiring the largest number of bits, then octal, and then hexadecimal, and then decimal. Sorry, this is going to be first decimal and then hexadecimal. This will be decimal and hexadecimal, because in hexadecimal we need 3 bits, in decimal we need 4 bits, in octal we need 5 bits, and in binary we needed 13 bits. Okay, so the correct option would be hexadecimal is given in option number C, decimal in B, octal in option number D, and binary in option number A. So that sequence should be C, B, D, A. So C, B, D, A, that means option number 3 is the right answer. but according to the answer key, they have mentioned that the ABC is right, but this is incorrect. What will be the right answer? CBDA is going to be the right answer. Next question is, for a JK flip-flop, they have given different condition in different options. Okay, and we have to select which one is correct from the given condition. Okay, so let us draw the JK flip-flop diagram. So this is the circuit diagram for JK flip-flop, and for that we have a truth table like this. So whenever clock is high, for different condition of JK, this is the condition of the output Qn plus 1, and if clock is 0, if J and K values are 0, Qn plus 1 is going to be Qn. So let us see the option. The first option says when J is 0 and K is 1. So when J is 0 and K is 1, Qn plus 1 should be 0. So A is correct. Let us check the B condition. When J and K both are 1. So when J and K both are 1, Qn plus 1 should be Qn bar. Okay, so here it is given as 1, so that is incorrect. So B option is incorrect. C option says Qn bar, which is correct. So C option is right. D option is when J is 1 and K is 0. So when J is 1 and K is 0, Qn plus 1 should be 1. So that is given in the option. So D option is also correct. E option says J is 1 and K is 0, then Qn plus 1 is 0. That is incorrect. So E option is incorrect. So from the given option, we have to select the right answer. So right options are A, C and D. So according to that, fourth option is the right answer. But as you can see in the answer key, they have given correct answer as A, C, E, which is absolutely wrong. So right answer is going to be option number 4, that says A, C, D are only correct options. Determine the output of the logic array given in the following figure. The cross represents the crosslink. So this is a logical array and we have to find the output for that, that is F, and the crosses are representing the connection link. So if we talk about what will be the output of this AND gate, so at the input we have applied A and this stands for B. So output will be A dot B. What will be output of this AND gate? Input is A and input is B bar. So that will be A dot B bar. Output of this AND gate will be, input is A bar and B. So output will be A bar into B. And input to this AND gate is A bar and B bar. So output will be A bar into B bar. Now these outputs are given to another AND gate and this has a crosslink at these 2 points. So these are the inputs for this AND gate. So what will be output F? That will be product of A dot B bar and A bar B. So if we open the bracket, that will be A dot B bar into A bar into B. Now we know A into A bar is 0. Similarly, we have B dot B bar, that will be 0. So the result of this expression is going to be 0. So F expression is 0 always. So that is third option, that is 0 here. But according to the answer key provided, that is A dot B bar plus A bar B. So this is incorrect. If this is correct, this should be a OR gate. Otherwise, if it is OR gate, then this expression is right. But if it is AND gate, then F will be equals to 0. So here they have given AND gate. According to that, F will be 0 only. Is the ripple counter shown in the following figure uses flip-flops that triggers on negative age transition of the clock pulse input. Is this counter a self-starting counter? Okay, so this is the diagram of a ripple counter and we have to identify whether it is a self-starting counter or not. Before that, we should understand one thing. What is a self-starting counter? In the counters, we have discussed what is valid states and what are invalid states. So suppose valid states are 2, 4, 5, 6 and then it goes again back to 2. Okay, so these are the 4 valid states that we have. Okay, this is just an example. Okay, and invalid states in this case is 0, 1, 3 and 7. So the counter should not enter into any of the invalid state. Okay, but if our counter enters into an invalid state, suppose 1, it goes into 3 and then it goes into 2. Then from 2 we know it will go definitely into 4, then 5 and 6, and it will go up again back to 2. So once it has entered into invalid state, if anyhow it is possible that it goes into some valid state, that is called a self-starting counter. So in self-starting counter, the counter is having the ability to move from invalid state into the valid state. So once it enters into valid state, it will remain in that valid state only. Okay, what are non-self-starting counter? In non-self-starting counter, what will happen? Once it enters into invalid state, suppose it goes into 1, then it goes into 3, then it goes into 7, and then it goes back again to 1. Okay, so this will remain in this loop only. So our counter, once it enters into invalid state, it will remain in the invalid state. It will never go into the valid states. That kind of counter is called as non-self-starting counter. So for the given counter, we have to identify the valid state and then we have to check whether it will go into valid state from a given invalid state. So let us understand this diagram. In this diagram, J and K are the inputs of the first flip-flop. So we will call it as flip-flop 0, flip-flop 1 and flip-flop 2. So this is having output Q0 and Q0 bar. This is having input as J1 and K1 and output as Q1 and Q1 bar. Now input of this flip-flop is J2 and K2 and outputs are Q2 and Q2 bar. Now if you look at this diagram, the clock, which is a negative age triggered clock. Okay, so the clock pulse is applied at the flip-flop 1 and the same clock is being applied at the flip-flop 2. So both will change their status whenever they find any negative age transition. What is negative age transition? Our clock is like this. Okay, so these flip-flop will respond whenever the clock moves from high state to low state. So whenever this kind of transition occurs, the output of flip-flop 0 and flip-flop 2 will change. And whenever it is finding a transition like this, they will not change their status. So they are active only for the negative age transition of the clock. Now come back to the question. So flip-flop 0 and flip-flop 2 are applied with the same clock, and output of flip-flop 0, that is Q0, okay, that is applied to one AND gate, and that is applied to the clock of the flip-flop 1. So that is why it is called as ripple counter. In ripple counter, output of one flip-flop will work as a clock for another flip-flop. Now here we have inputs as 1 and 1. So whenever we have a condition when J is equals to 1 and K is also equals to 1, we know output Qn plus 1 will be Qn bar. That is, it will be in toggle mode. So this flip-flop is working in the toggle mode. So for every negative edge transition, it will change its status. Now output of this AND gate will be Q1 into Q0, or we can say B dot C. Okay, so we will talk in terms of Q1 and Q0 only. Now let us solve this question. So Q1, Q2, Q1 and Q0. Initially we assume that the flip-flops are cleared. Okay, so flip-flops are cleared, so they are all 0. Now when it finds a clock, first clock we apply, and it is having negative age transition. In that case, flip-flop 0 will change its status from 0 to 1. Now this Q0 output is working as a clock for Q1, and it is having positive age transition. So it will not affect the output of Q1, so that will remain as it is, so it will be 0. Now 0 into 1 will be 0, and hence we can say J is Q1 into Q0, so that will be 0, and K will be 1. And whenever this is the condition, Qn plus 1 will be 0. So output of flip-flop 2 will be 0. Now in the second clock, in the negative age transition, this Q0 will again change from 1 to 0. And now this is having a negative age transition from high to low. So it will change the status of Q1. So it will change from 0 to 1. Now input of J will be again 0 and K will be 1. So we know Qn plus 1 will be 0. So this will be 0 again. In the third clock, in the negative age transition, it will change its state from 0 to 1. Now it is positive age for Q1, so it will not change its state, it will remain 1. Now AND operation of these two is 1, so J will be 1 and K will be 0, and whenever this is the condition, output will be 1. So output will be 1 in this case. Now in the fourth clock, in the negative age transition, this will again change from 1 to 0, and this is working as a negative age for flip-flop 1, so it will change its status from 1 to 0. Now AND operation of these two is 0, so J is 0, K is 1, so our output is going to be 0. And now you can see we have started from 0, 0, 0 and we have come back to 0, 0 again. So this counter is moving in different state like this: 0, 0, 0 to 0, 0, 1, then 0, 1, 0, then 1, 1, 1, and from 1, 1, 1 again it goes back to 0. So these are our 4 valid states that we have. And what are invalid states? We can write the decimal equivalent of these. So this is 0, 1, 2 and 7. So what are invalid states? Invalid states are 3, 4, 5 and 6. So we have to check if our counter initiated from any of the given invalid state, does it go back to valid state. So let us consider it is in invalid state, that is 5. So let us make this is Q3, Q1 and Q0. This is 1, 0, 1. So if it is started from invalid state 1, 0, 1, now if we apply negative age clock to the Q0, it will change its state from 1 to 0. Now this is working as a negative age for flip-flop 1, so it will change its state from 0 to 1. Now AND operation of these two is 0, J value is 0 and K value is 1, so output will be 0. And now 0, 1, 0, 0, 1, 0 is a valid state. So it has started from invalid state and now it has entered into valid state, and once it enters into valid state, it will remain in that loop only. So it is a self-starting counter. So first option is going to be right answer. So this is how you have to check whether a given counter is self-starting or not. Next question is match the column type of question. It is very easy question, but there is some error in the answer key. So let us discuss this question. So they have given different gates. So this is negative OR. Negative OR means NOR gate. And what is the truth table of NOR gate? NOR gate says whenever one of the input is 1, output should be 0. So that is matching with the option number 1. So whenever one of the input is 1, output is 0. So this is a NOR gate. So A is matching with option 1. Now exclusive NOR. Exclusive NOR means XNOR gate. And XNOR gate says whenever inputs are same, output should be logic high. Okay. So from the given option, we can say the third option. Here we are having same inputs, then only output is logic high. So this is XNOR gate. So B is matching with the third option. C option says exclusive OR. Exclusive OR means XOR gate. And we know XOR gate means whenever inputs are different, then only output is going to be logic high. So in the table number 4, you can say whenever inputs are different, 0, 1 or 1, 0, then only output is logic high. So this is C option is matching with the fourth option. Now D, negative AND. Negative AND means NAND gate. In NAND gate, what happens? If one of the input is 0, then output will be logic 1. So according to that, in the second table, you can see whenever one of the input is 0, then output is logic 1. So D option is matching with the second. Okay, so this is going to be